Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutewa Sos Ugobela Maths. And without any further ado, let's look at these questions that we got here. Ah. Okay, so we have the Eastern Cape Province paper from the Amathole West District, grade 11 Physical Sciences Control Test, which was written in 12 September 2023. Marks 100, time is 2 hours. So we'll just be going through this question paper so that we get a feel of how to answer question papers, and then you get the skill of how to actually conserve your energy as you are going through it. So we have 2 hours, and hopefully we'll be done with this paper in less than 2 hours, right? Okay, so question 1 says we have multiple choice question. Obviously, various options are provided as possible answers to the following questions. Each question is only one correct answer. Write only the letter A to D next to the question number. That is, if you feel that your answer to 1.1 is D, you'll just write 1.1 D in your answer book, right? But then obviously we don't have an answer book, so we'll just try to go through these questions here. Now we have 1.1. It says the minimum amount of energy needed for a reaction to start is called. So for this one, we don't even have to necessarily look at all those options. We know that the definition for that is, or the term for that definition is the activation energy. So 2 marks. Now 1.2 says which one of the following statements about a chemical reaction is correct? The actual yield of a chemical reaction is usually A, is it equal to the percentage yield? B, greater than the percentage yield, C, less than the theoretical yield, or D, greater than the theoretical yield. Now, if we do a recall of the formula here, we know that we have percentage yield is equal to the actual yield, and then over the theoretical yield, and then multiply that by 100. Now, I will just from here eliminate A and B, because A and B wouldn't make any sense, mainly because the actual yield is mostly given as the mass, and then the percentage yield is just a representation of the actual yield to the theoretical yield in a form of a percentage. So we cannot really compare our the product of all of this to the actual yield, right? So comparing the percentage yield to the theoretical yield in any way is just not feasible. So A and B won't look at that. What we can compare is the actual yield and the theoretical yield, right? So this is a percentage and these are masses. There is nothing to compare there. Now, C says less than the theoretical yield. D says greater than the theoretical yield. Now, what we normally know with these questions is that our percentage yield should be less than 100%. And if it has to be less than 100%, we know that this here has to be what we call a proper fraction. Proper fraction is whereby if we have this being represented as A over B, then our A value, which is the numerator, should be less than our B value, which is the denominator, right? So the actual yield in this case is always less than the theoretical yield. Because remember, actual yield is what we get when we actually perform that chemical reaction. But then theoretical yield is only based off calculations without any consideration of what might happen when you actually perform the chemical reaction, right? So there might be any spillages of your reactants. There might be some of the particles escaping, let's say gas particles would escape the reaction vessel, of course. So now, obviously, all those factors would contribute to your actual yield being less than the theoretical yield, right? So in most of the cases, we know that that would be true. So C. Right. So as we have proven that we have never calculated a percentage yield, and we found that it was greater than 100%. Okay, so now we have the 2 marks in the bag, just like that. Let's proceed. Now we have 1.3. It says, which one of the following statements is correct for an endothermic reaction? A what? An endothermic reaction. Right? So note that endothermic reaction, the properties is that it absorbs heat. So we bear that in mind. The temperature of the surroundings increases. If endothermic reaction actually absorbs the heat, then we wouldn't expect the temperature of the surroundings to increase. Because remember, absorption of heat is related with the surroundings being cold. So the temperature would have to decrease in that case. So not quite correct. B, the enthalpy change for the reaction is negative. Now we know that is only true for an exothermic reaction, right? So we wouldn't consider that one. That means we will say our enthalpy change here would have to be greater than 0, mainly because we know that enthalpy change is indicated by what? Energy of the product minus energy of the what? Of the reactant, whereby the energy of the product is always greater than the energy of the what? Of the reactant. So if the energy of the product is greater than the energy of the reactant, then we know for sure that our enthalpy cannot be negative. So also this one is not correct. Now C, heat flows from the surroundings into the system. Heat flows from the surroundings into the system. What do we know about the endothermic reaction? It absorbs the heat. So this perfectly describes that. Heat flows from the surroundings into the system, which then leads to the surroundings being cold, the surroundings decreasing in temperature, right? So definitely C. Now, even if we can look at D, the enthalpy of product is less than the enthalpy of the reactants. Nope. It's actually the enthalpy of the product being greater than the enthalpy of the reactants. So C is correct. We have 2 marks in the bag again. Then, okay, let's proceed now. So for 1.4, it says consider an incomplete chemical equation below. Which one of the following is represented by X in the above equation? Now, looking at this, we can see that the zinc nitrate is a salt, and then this is water, and then this is carbon dioxide. Okay, this is a question obviously on acids and bases, and we know that an acid, when it reacts with a metal carbonate. So this is what we know from our notes on acids and bases. When an acid reacts with a metal carbonate, the products produced are salt, water, and carbon dioxide, which we can see the salt is the zinc nitrate. Now, what is this metal carbonate that we reacted with this acid? Now, which one is the acid? This is the acid. It is known as what? Nitric acid. It's very important that you know that chemical formula there. It's nitric acid. So that means X here would have to be that metal carbonate. Now, which one represents a metal carbonate here? Definitely not this one. Definitely not that one. So this is hydroxide, obviously. And then this is not really a carbonate. So this is the metal carbonate, actually. So this is metal hydrogen carbonate. But then we said this occurs when we are reacting an acid with a metal carbonate. So the answer has to be what? A. Nice one. So we are fine with that. And then now let's go to 1.5. The number of ions present in 3 moles of magnesium chloride is, okay, so let's see. So this might need a little bit of calculation. So if we can pull up the formula here, N is equals to N over NA. We know that this formula here, the big N there, can be used to calculate number of particles, can be used to calculate number of atoms, can be used to calculate number of molecules, can be used to calculate number of ions. So this is a multi-purpose formula, right? But then never use, don't use that formula. That big N actually is not for the number of moles. It's number of molecules. The number of moles is the small n, obviously. So you'll put your 3 here and then N over Na, which is Avogadro's constant, 6.02 times 10 to the exponent of 23. So obviously Avogadro's constant says that 1 mole of any substance contains 6.02 times 10 to the exponent of 23 particles, right? So if it's 3 moles, that means it must contain 3 times that. So now we're going to do the calculation. 3 multiplied by 6.02 times 10 to the exponent of 23. Right, then we get 1.806 times 10 to the exponent of 24. Right? But then that's not your answer. As even when we are looking at this, there is no answer like that here from the option. This is not what, this is 1.806, and here we only have 1.08. So this is not the final answer. Now, what must we consider? Note that they said the number of ions, not the number of particles. So with ions, that means we have to take this, put it in water, and then we know that it will dissolve to magnesium 2 plus ion, and then also it will dissolve to what? Cl minus. But then the 2 here indicates that we actually have 2 ions of the chlorine, right? So we have the 2 ions of the chlorine like this. So 2Cl minus. So all in all, how many ions do we have in magnesium chloride? It's actually 3 ions. So what must we do if we want to calculate the number of ions present here? We must take this number and multiply it further by 3 so that we can find out the number of ions present. So if we take that and multiply it by 3, we have 5.418 times 10 to the exponent of 24, which our option here would have to be what? B. Okay, so nice one. All right, then 1.6 says, according to the kinetic molecular theory, molecules of different gases at the same temperature always have what? Do they always have the same pressure? Do they always have the same volume, kinetic energy, or average kinetic energy? Now, from the KMT, we know that temperature is actually directly proportional to the average kinetic energy. So EK average, right? So we know that temperature is directly proportional to the average kinetic energy of the particles, right? So hence, when we increase the temperature, we say the average kinetic energy of the particles also increases. Now, when you look at option C and D, you can see that there is a little bit of trying to play mind games there, because C just simply says kinetic energy, and then D says average kinetic energy. Because we are looking at all the particles as a whole, it would have to be the average kinetic energy. So the energy being possessed by each and every particle, and then added together and divided by how many particles are in that reaction vessel. That gives us the what? The average kinetic energy. So our answer would have to be D instead of C. So you need to be very careful of your content there. Now, 1.7 says, two different gases of the same volume at STP will have the same, what is it, mass, density, molar mass, or the number of molecules. Now, if we have to define Avogadro's law, it says, obviously, the what you call the gases that the volume occupied by two different gases, or okay, so two different gases of the same volume at STP. So at STP, two different gases will usually have the same number of molecules, right? So kind of forgot how to actually define that. But then somewhere, if you want to check the definition, it has same number of molecules, right? So I'll have to check that one up. Okay, so let's proceed. Let's proceed. Then we have question 2. Now it says we have our Boyle's law ideal gases. Then we are given a volume versus pressure graph. A fixed mass of oxygen is used to verify one of the gas laws. The results obtained are shown in the graph below. Write down a mathematical expression in symbols for the relationship between the variables shown in the graph, right? Shown in the graph. So what are we going to do now? We know that the relationship between volume and pressure, according to Boyle's law, is inversely proportional. So you can either indicate that mathematical relationship by saying pressure is inversely proportional to volume, or even if you put it like this, guys, this is still the same thing, as long as you are indicating that there is an inverse relationship there, right? So pressure is inversely proportional to volume, or volume is inversely proportional to pressure, one and the same thing. Give the name and state the law and state the gas law investigated. So 3 marks. We must give the name of the law and then also state it. So we know that's definitely Boyle's law. Then not only should we say Boyle's law, but then we should also define it. So Boyle's law, right? And then it states that the pressure of an enclosed gas is inversely proportional to the volume it occupies at constant temperature. Very important for you to even mention that control variable at constant temperature, right? So obviously you're going to earn yourself a mark for saying Boyle's law and then earn yourself an extra 2 mark for having to define that. Okay, then 2.3 says, explain the relationship in question 2.1 in terms of the kinetic theory of gases, right? So this is how we're actually going to put it. So let's find some space here. So we're going to say when the volume of the container is decreased, the particles will be closely packed. We know that, right? And then hence the particles will collide more frequently with the walls of the container, leading to an increase in pressure. Leading to an increase in pressure. Right, so that's it. When the volume of the container is decreased, the particles will be closely packed. Hence, the particles will collide frequently. I said frequency. Frequently with the walls of the container, leading to an increase in pressure. Right, so that's how you actually put it. And then, yeah. Okay, then 2.4 says what? Write down the 2 variables that must be kept constant during this investigation and briefly describe how this is done, right? So we know that it's obviously the mass of the gas, the mass of that enclosed gas, mass of the gas. Ensure there is no leakage. Ensure there is no leakage or escaping of the gases. So ensure that it's tightly sealed, right? Then another thing that should be kept constant is obviously the temperature. We know these 2 are the ones that are normally kept constant. And then temperature, you just gradually increase the pressure. Without having much effect on the temperature. Without having much effect on temperature. Right, so can keep the temperature constant by just gradually increasing the pressure. So don't increase it too much, just gradually increase it slowly, and then that will not have much impact on the temperature. Right, so that's all you were supposed to say there. So a mark for mentioning, so mark each for just mentioning mass of the gas and temperature, and then you'd have another mark if you went further to explain how you would actually keep those 2 constant. Okay, so make sure you know that. Know that my handwriting is kind of chopped, but then hoping it's visible enough. Okay, so from the graph, write down the volume of oxygen in centimeter cube when the pressure is 120 kilopascals. So obviously, this needs us to be able to find the interval here. So normally, this is what you do. You know that with this type of graphs, you have 10 blocks here dividing here. So each and every big block here has 10 smaller blocks. So if you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now if you want to actually find out how what each of this block actually represent in units, you can just go 50. So the first number that you're going to see here divided by how many blocks you have counted, which is 10. So if you say 50 divided by 10, you will get 5, meaning each and every block is representing 5 units. So this would be 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Right, so that's how it would actually go. So if you want to locate 120 kilopascals, 120 kilopascals, then it would be 105, 110, 115, and then 120. So what you're going to do here is from that, you're going to draw a straight vertical line until it hits that curve, right? So where it touches the curve, you will then have to bend it so that it goes straight to your value there, which is what? The 30 centimeter cube, right? So now you have the 30 centimeter cube, and then we can say that our value here is 30 centimeter cube, right? Now others, maybe because of their pencil or how they do it, maybe they might land on 31, right? So, but then we have 30 centimeter cube right there. Now, 2.6 says, using the graph and the information provided, calculate the pressure in kilopascals exerted on the gas when it is compressed to 5 centimeter cube. Now, you will remember that we already have 30 centimeter cube here. So we can just continue with that value there to say, okay, to calculate that, we obviously need the formula P1. V1 is equals to P2 V2. This is the one that we normally use for this type of questions, right? So our pressure one, we want to take it as the 120 kilopascals. So no conversion of any type here. Then you just put 30 there. Now we are looking for pressure number 2 when we are given that the volume here is 5 centimeter cube. So obviously what you need to do at this point is divide both sides by this 5. And then your pressure number 2 becomes what? 720 kilopascals, right? Then there you go, 4 marks. Okay, so where will you get your marks? Mark here for substitution, mark here for formula, and then 2 marks for substitution, and then a mark for the correct answer, obviously with the correct SI unit, right? So nice one, nice one. Then that's how we'd be going through our Boyle's law. So we still have 2.7. Write down the 2 conditions under which oxygen will deviate from ideal gas behavior. We know that a real gas deviate. So oxygen gas is what? Is a real gas. A real gas deviate from ideal gas behavior in during which conditions? So we know when there is high pressures. Hence, we did say that you must increase the pressure only gradually. And then also what? Low temperatures. We know that there is no gas when the temperature is low. Gases form at very high temperatures, right? So when you have a low temperature, we say that your gas will liquidify. Or is it liquefy? Liquidify. I don't know. Okay, so 18. 18 marks just like that. 18 marks just like that. So question 3, consider the reaction represented by the equation below. We have carbon dioxide reacting with 2 molecules of water to give us CH4, which is methane, and then 2 molecules of oxygen gas. During the reaction, the temperature of the reaction mixture is decreased. So that's what they're telling us there, that they've decreased that. Now they say define the term enthalpy change. What is that? So we say enthalpy change is the same as heat of reaction. Do not be amazed, right? So the same definition that we gave for heat of reaction is the same as enthalpy change. Heat of reaction and enthalpy change is actually one and the same thing, right? So the pressure, we say it's the amount of heat or energy absorbed right? Absorbed if it's endothermic, or released if it's exothermic in a chemical reaction. In a chemical reaction. So this is the amount of heat or energy absorbed or released in a chemical reaction, depending on whether it's exothermic or endothermic. If it's exothermic, obviously the heat or the energy will be released. If it's endothermic, the heat or the energy will be absorbed, right? So that is it. Then 3.2, does the enthalpy change for this reaction have a positive or negative value? Explain the answer by referring to the energy involved. Right. So this is what we actually want to do. So this actually requires us to perform a little bit of calculation in terms of what we are given. We are given the bond energies here. And then we are given that the double bond between carbon and oxygen gives us 602 kilojoules per mole, right? But then here we can see that if we can draw the carbon here and then indicate the bonds here, they would actually be like this. So that means we have 602 for here. So this would, to break this bond, would take 602 kilojoules of energy. And also again, to break this bond here would also take the same energy, right? So we have two double bonds of the carbon to oxygen. Then this would be indicated by 2 multiplied by what? 2 multiplied by 602. So let's indicate that all of these are reactants. So the 2 here are reactants, and these are the product. Then we go to this one. This is 2H2O, right? But then here we can see that we have our OH. So this is OH, and then OH like that, right? So this is what? 459. 459 to break those bonds, right? Then, since there are 2 molecules of that, I would have to say multiply that by what? By 2. So I am done for the reactants. Let's add up the sum to that. 2 multiplied by 602, it's 1,204. 456 multiplied by 2, that's 980. If we add those ones together, we get 2,122 kilojoules per mole. So this would be the energy of the reactants. Okay, now let's come to the products. Products, we have this here, CH4, but then the bond to CH, C to H, only takes 411. So, but then if we are to indicate that, there would be 4 bonds around the carbon. So 1, 2, 3, 4, and then you'd have to break all of that. So that means we'd indicate that by saying 4 multiplied by what? 411, because there are 4 bonds that you'd need to break. Then what about this one here? We have the double bond oxygen here, which is only that one. But then we have 2 molecules of that, so that would be 494 multiplied by 2. Now if we say 4 multiplied by 411, that's 1,644. And then here 494 multiplied by 2, that's 988. Now when we add the 2, we get 2,632 kilojoules per mole, right? This is the energy of the product. Now, looking at the energy of the product and the energy of the reactant, we can see that the energy of the product is actually greater than the energy of the reactant, which suggests that this is what? An endothermic reaction. An endothermic reaction. And if this is an endothermic reaction, that means our enthalpy change is what? Greater than 0. Even if you were to follow enthalpy changes, energy of the product minus energy of the reactant, by simply saying 2,632 minus the 2,122, you would actually find a positive value there. So which suggests that your enthalpy change is positive. There we go. So, okay, so we are going to say positive. Our answer is positive. And the reason is enthalpy change is greater than, actually that's what we were asked. So the reason is that energy of the product is greater than the energy of the reactants. Okay, so also did some calculations there to prove that. So you do not necessarily have to show the calculations. They just want you to explain that in words, right? Energy of the product is greater than energy of reactants. So they will give you 2 marks for that. 2 marks for saying that, and then a mark for saying positive. Okay, nice one. Nice one. Then 3.3 says, sketch a labeled potential energy versus cost of reaction graph. For this reaction on the graph, show the position of the reactant, show the product, the enthalpy change, and the activation energy. So this is what you're going to do now. So you would have your sketch. Okay. This. Then obviously what you write down here is cause of reaction. Then what you want to write here is potential energy. In kilojoules per mole. Right. And then your graph or your sketch should look like this. Remember, it's endothermic reaction. If it's endothermic reaction, then it goes like that. So these are your reactants. Carbon dioxide plus 2H2O. And then here you have your product, CH4 plus 2O2. Right. And then all the way from the reactants to the activated complex, that's your activation energy. So EA. But then in between these two here, the reactants and the product, that's where you find your what? Your enthalpy change. Right. So, yep, that's all you indicate. So you have shown the position of the reactants, check. You have shown the position of the products, check. You have shown your enthalpy change, check. You have shown your activation energy, check. You have labeled your axis, right? Check. And then the shape of the graph is correct. It's an endothermic graph. Check. 6 marks. Okay, nice one. So that's how you bag those marks, guys. All right, question 4 now. The chemical reaction for the production of the drug aspirin from 2 compounds X and Y represented by a balanced equation below, right? So there we go. It says we are given compound X and Y, and then the product there is aspirin, and then we have water as well. A chemist reacts 14 grams of compound X with 10 grams of compound Y. Define the term limiting reagent. So what do we say is a limiting reagent? We say this is a substance that is completely used up in a chemical reaction, right? So the substance that will be completely used up in a chemical reaction is known as the limiting reagent. So 2 marks for that. So 2 marks for that definition. Now they say 4.2, perform the necessary calculations to determine which of compound X or compound Y is the limiting reagent. Right. So let's focus on 4.2 now. Okay. So do we have anywhere where we can perform that calculation? Okay. I think here would be good. So note that we have 14 grams for this one. So if we can start by calculating the number of moles, remember the first step is we calculate the number of moles of each of those, right? So number of moles of C7H6O3. And then this is mass over the molar mass. Now our mass is what? 14 grams for this one. Then molar mass, 7 multiplied by 12 plus 6 multiplied by 1 plus 3 multiplied by 16. So that's 138. Then if we say 14 divided by 138, we get what? 0.10 mole. Okay. Then number of moles of C4H6O3. And then that's mass over the molar mass. Now we have what? 10 gram divided by 4 multiplied by 12 plus 6 multiplied by 1 plus 3 multiplied by 16. That's 102. Then what's 10 divided by 102? Again, we get 0.098, so which can be converted to 2 decimal places, rounded off to 2 decimal places, 0.10 mole. So they have the same number of moles. But then looking at the ratio of reaction, we can see that the ratio of reaction from X to Y, so X to Y, the ratio of reaction is that compound X has 2 and then compound Y has 1. If we decide to make this the reference to compare with, so this will be the reference whereby we'll be comparing. Reference. Then we have to say, if I put 0.10 mole here, how much of this is actually required? So this is available. This is what we have available from that. Now we want to calculate how much of this should actually react so that it reacts with all this 0.10 mole. Then when we cross multiply, we get 2x is 0.10, divide by 2, then our x is 0.05 mole. Meaning, this is what is required. But then this is what we have available, right? So we do not actually need to react all of this. Now, looking at the reaction, the reaction ratio already tells you, if this is going to bring 1 mole, this should bring 2 moles. This is going to bring 5 moles. This should bring 10 moles. So obviously, which one will be completely used up first? It is the one with the bigger ratio here. So the one with the bigger ratio would have to contribute more. In that 10, it will be used up completely. It will be used up first, right? So that means in this case, we're going to say this one is actually in what? In excess, meaning that that one there has to be what? Limiting. So in other words, our conclusion is that C7H6O3, which is this compound X, is the limiting reagent. Now, how do I make these conclusions, guys? Remember, when we were doing this topic, I said always note this. If the number of moles available is greater than the number of moles required, then that means substance is in excess. So that particular substance is in excess, which is the what? The substance would have to be the reference. Everything would have to be based on what you make the reference. Again, we know that if it is the opposite now, and then we actually find that the number of moles available is actually less than the number of moles required, then it would mean that that particular substance is the limiting reagent, which still we are talking about your what? Your reference, right? So note, these are your conclusions here. This is how you decide which one is the limiting reagent, which one is the excess reagent. Because now the available was greater than the required, we said this one that we made the reference has to be in excess, which means if this is in excess, then it goes without saying that the other one is the limiting reagent. Because remember, in a reaction, you always have one excess reagent and one limiting reagent. They can't both be limiting reagents. They can't both be excess reagents. So if you prove that one is in excess, then that means the other one is limiting. If you prove that one is limiting, that means the other one is in excess. That's how it works. Okay, nice one. And then 4.3 now, we are to calculate the percentage yield. So they say the actual mass of aspirin obtained is 11.5 gram. right? So it's taking us back to that question we were answering on multiple choice question. So always note it when I say that your multiple choice questions are actually detailing what will be in the exam paper, right? So if you actually go through the questions, you apply those concepts, it would be much easier for you to then answer your multiple choice questions, which I normally advise that go back to your multiple choice question as the final as the final question that you actually answer in an exam paper. Do not waste much of your time trying to start by answering multiple choice questions. But then, however, if you feel you can do it, you can actually do it. But then, to save time, I normally advise that look at your multiple choice questions as the final question. And then calculate the percentage yield of aspirin. Now, what is the steps that we need to take into this? Now, always note this. This is the aspirin, right? And then we've already found that X here is the what? Is the limiting reagent. Remember, if we want to calculate the percentage yield, it always goes like this. Remember, the order is that once you find the limiting reagent should lead you to being able to calculate the theoretical yield, right? And the theoretical yield should lead you to then being able to calculate the percentage yield. The order is always like that. So now that you have found the limiting reagent, it means in order to find the number of moles of the aspirin, you would have to relate the limiting reagent to the aspirin. Do not, and I repeat, do not compare the molar ratios of the excess reagent to the one that you want to calculate the product. It's always the limiting reagent that will tell us of the theoretical yield. The limiting reagent is the one that determines the extent of the reaction. If the limiting reagent comes to completion, then there is no longer any reaction. But then you can still have your excess reagent there. But then still the reaction will not continue. Okay, so which is why the limiting reagent is the most important. So now that we've found the limiting reagent, we'll say, what is the ratio of C7H6O3 to the ratio of the aspirin, which is C9H8O4? Find that the ratios are what? 2:2. So when we're talking about ratios, we are talking about the coefficients. But what do we know? Once the ratios are the same, it means even the number of moles will be the same. Now, what number of moles are we comparing? The ones available. So when we calculated this in 4.1, we found that the number of moles available for this was 0.10, meaning also that must carry the 1.10 mole, right? Because same ratios breed the same number of moles. If you are to simplify the 2:2, it will simply become 1:1, meaning they share the same number of moles. So this is step number one. You first find the number of moles of that. Step number two, this is when now you calculate the what? The theoretical yield. The theoretical yield is the mass, guys. This is the mass. And then how you're going to do it? N is equals to mass over the molar mass. Put your 0.10 and then mass over the molar mass of what? Remember, the reason we even found the number of moles of this, it's because we are looking for the mass of that aspirin, which is the one that we are trying to calculate the percentage yield of. So now, when I say C9, that will be 9 multiplied by 12 plus 8 multiplied by 1 plus 4 multiplied by 16, right? And then we get what? 180. So 180. When we cross multiply here, our mass will be what? 18 grams. So this is the theoretical yield. Then number three, to then calculate the percentage yield, let's pull out the formula. Percentage yield is equals to what? The actual yield, which is, we did say that normally we are given. And then again, coming back to that multiple choice question, can you see what we answered there? We said the actual yield must be less than the theoretical yield. And exactly, we can see that our actual mass, which is the actual yield, is actually smaller than the what? Theoretical yield. So obviously, it's because this is only based on calculation and not on really performing the reaction. So 11.5 divided by 18 multiplied by 100. So 11.5 divided by 18 multiplied by 100. This is going to give us what? 63.89%. There we go. 63.89%. And that becomes your what? Your percentage yield. Nice. So again, we can see that our percentage yield will not be equal to the actual yield. Okay, nice. So 12 marks in the bag, just like that. Again, let's continue with question 5. So we have a nice deal of a question here for 8 marks. And then question 5 says, in order to determine the empirical formula and molecular formula of a compound CXHY, a certain mass of compound is burnt completely in excess oxygen to produce 41.1 gram of carbon dioxide and 19.35 gram of H2O as the only products. Then 5.1.1 says, define the term empirical formula. So we already know that definition. We say this is the simplest whole number ratio of all the elements, or others say atoms, of all the elements in a compound. So whether you say elements or atoms, it's all the same thing, right? Simplest whole number ratio of all the elements in a compound. So 2 marks just like that. Then 5.1.2 says, use relevant calculations to determine the empirical formula of the compound. Now we know that empirical formulas are mostly like 5 marks, 6 marks question. But then why is this one 8 marks? When we read that, we will actually find out that we were not actually given the masses of the elements. Remember too, as we defined, empirical formula is the simplest whole number ratio of all the elements, each individual element. So right now we can see that we are actually given the masses of the compounds. Now we don't calculate empirical formula on compounds. We calculate empirical formula based on each element. So that means here, from this carbon dioxide, we would have to find out what is the mass of carbon. From this H2O water, would have to find out what is the mass of hydrogen. Now, when we found out the mass of carbon and the mass of hydrogen, that's when now we can actually calculate the empirical formula. So now what are we going to do? We are going to pull up our grade 10 percentage composition knowledge, right? So in percentage composition, we normally used to do this, right? To say that if we want to find the percentage composition of carbon dioxide, we would have to look at carbon. What is the mass of carbon? So mass of carbon from the periodic table. So let's say to then calculate the mass of carbon. So I will do percentage composition, but then now in terms of mass. So mass of carbon is 12. And then the molar mass of the whole carbon dioxide, that would be 12 multiplied by 2 times 16, which is 44 grams per mole. So I will say 12 divided by 44. But then 47.1 gram makes up 100% of the carbon dioxide. So if we want to find out what is the mass of the carbon only, we'd have to say 12 over 44 multiplied by the 100% of all this compound, which is the 47.1 gram. Now let's see the percentage composition or the mass composition. In this case, we will call it the mass composition because we are calculating in terms of mass. Then multiply that by 47.1. And then we actually find that the carbon is contributing what? 12.85 grams, rounded off to 2 decimal places. Right, 12.85 gram of the mass is actually making up the carbon dioxide, meaning the rest is only just oxygen. Now, okay, we have found the mass of carbon, which is what we need in order to calculate this. Now, what else do we need? We don't need the oxygen, we need the hydrogen. So we don't see any hydrogen on this one, but then we do see a hydrogen here. But when we come to this one, we need to be careful, right? With this one, we can see that we have 2 hydrogens. So the mass of the hydrogen would have to be what? Hydrogen is 2 atoms, and then the molar mass of these 2 atoms is 2, right? Because hydrogen each is 1 gram per mole. And then H2O in total is 18 grams per mole. multiply that by the 100% of the H2O, which is the 19.35 grams, right? And then we find that the mass of the hydrogen that it contributes to the making up of water is only what? 2.15 grams, right? So now we have found the mass of hydrogen, we have found the mass of carbon. At this point, we can then calculate our empirical formula without any stress, right? So at this point, when we've done all that, that means we can now continue in peace. We can now continue in peace to say that, okay, let's calculate now. Let's calculate. So step number one is to calculate, obviously, the number of moles of each element. So mass over the molar mass. And then this is going to be what? 12.85 divided by 12. Then 12.85 divided by 12, that's a 1.07 mole. And then let's see for the hydrogen. Mass over the molar mass. And then we have a 2.15 divided by 1, which will give us 2.15 mole. Now, the second step is to do what? Divide by the smallest number of moles, which is this. So to find the ratio of carbon, it's 1.07 divided by 1.07. To find which is going to give us what? 1. Then to find the ratio of the hydrogen, there will be 2.15 divided by 1.07, which is going to give us rounded off 2, right? So that means our empirical formula right now would have to be what? So empirical formula is CH2, right? That would be the empirical formula, the simplest whole number ratio. So nice, 8 marks like that. So we needed to first start by calculating the mass of the carbon, the mass of the hydrogen, using percentage composition or mass composition of those elements. Then from there on, we continue with our empirical formula as we know it, right? So that was a little deviation there. Okay, so make sure that you note that. That was a very nice question there. Okay, then 5.1.3, they say the molar mass of the compound is 28 grams per mole, determined by using calculations the values of X and Y. Now, obviously, what they're telling us here is that we must find the molecular formula of the compound, right? So we have the empirical formula is CH2. If we want to find the molecular formula, first we calculate the molar mass of the empirical formula. We say 12 plus 2 multiplied by 1, which is going to give us 14 grams per mole, right? But then what do we do now? We're going to say 28 divided by this 14, and then we get 2. Now, what are we going to do with this 2? This is the 2 that we multiply the subscript with so that we can find the what? The molecular formula, right? So molecular formula now will be 2 multiplied by 1, which will be C2. 2 multiplied by 2, which will be H4. So meaning, in other words, X and Y are the ones that we get here. So that means X will be equals to 2, and then the Y will be equals to 4. Hallelujah. Okay, so that's how we were supposed to go about that one. Easy peasy. Okay, so make sure that you also note that. So unfortunately, if you were not able to get your 5.1.2, could have been a challenge also to get 5.1.3. So you could have lost like 11 marks in total. Okay, then a sample of impure calcium carbonate limestone of unknown mass required a continuous supply of strong heat to decompose according to the following equation. After the completion of the reaction, 11.7 gram of calcium oxide was produced. The percentage purity of the calcium carbonate is found to be 80%. The percentage purity is 80%. Now they say 5.2, calculate the mass of the impure calcium carbonate. So now they want you to calculate the impure calcium carbonate. Now we do know that the formula for percentage purity goes as mass of the pure substance over the mass of the impure substance multiply by 100, right? So that means in this case, we'd have to calculate the pure substance. We are already given the percentage purity, and then we'd have to do our math here in order to find the mass of the impure, right? So it's still the same calculations that we are following, even if we are doing percentage purity. The only difference here is that this time around, we are given the percentage purity, and we should calculate the mass of the impure, which in most of the cases, it is usually given. But then this is more of a tricky question only on that part that they now gave you the percentage purity instead of the mass of the impure. So it's not really a train smash. Let's just follow our calculations the way we know how. So number one, after the completion of the reaction, 11.76 gram of calcium oxide was produced. This is where we're going to start. Step number one, we know it is always to calculate the what? The number of moles, right? So number of moles of calcium oxide, we're going to say mass over the molar mass, which is 11.76 over calcium is 40. So 40 plus 16, that will give us 56. And then 11.76 divided by 56, this will give us 0.21 mole. Now, what is the next step? The next step is obviously to compare that to this calcium carbonate, because remember, we are trying to calculate for calcium carbonate. This is not calcium carbonate. This is calcium oxide. This is what we are trying to find. The impure calcium carbonate. This is the impure calcium carbonate. So we are going to say the ratio here says for calcium oxide to calcium carbonate, the ratio is just 1:1. The ratio is 1:1. That means as I found 0.21 mole here, also that must be 0.21 mole, right? So which means now I can calculate the mass of the calcium carbonate. But this mass that I'm calculating, what is it actually? The mass that I'm calculating is actually the mass of the impure, because the mass of the impure is the one that reacts. Remember, the impurities will not react, which now leads to the fact that your impure substance will not all react. Some of the impurities will be left, right? So now what we are actually calculating here is the mass that would have reacted, which is the pure substance. Then this is N is equals to mass over the molar mass. 0.21 is equals to M over the molar mass of calcium carbonate is calcium is 40 plus carbon is 12, and then multiply plus 3 multiplied by 16. This will give us 100 grams. Then 0.21 multiplied by 100. This will give us a mass of what? 21 grams, right? So this is the pure, right? They said the percentage purity of the calcium carbonate is 80%. 80%. Now let's come to this formula now. This is the real deal. Percentage purity is equals to the mass of the pure is 21. Now we don't know the mass of the impure. Let's say it's X, and then multiply that by 100. But then the percentage purity is what? 80%. So we're just going to write 80 here. And then we just cross multiply here. That is 80x is equals to 21 multiplied by 100. So this will give us 2,100. Then we can divide both sides by this 80. And then we find that the mass of the impure is what? Is actually 26.25 grams. So from the 26.25 gram, only 21 gram actually reacted. So in other words, only 21 gram was actually the pure sample. And then this is all the what? The impure sample. Okay, so that's how you go about it. So 6 marks. So as you can see, there is nothing that changed. Still, your step number 1 is calculating the number of moles. Step number 2, compare the molar ratio. Step number 3, calculate for the required value. And then your step number 4 is obviously now performing your calculation with the percentage purity formula. So your stoichiometric steps, they never change. Okay, so 6 marks in the bag just like that. And then, yeah, this stoichiometry, yeah, this question 5 was really the A. A lot of those questions there. Imagine you have the 8 marks, the 3 marks here, then the 6 marks, and then another 6 marks. Hey, this was tough. Hey. In an experiment, a learner added 1.5 gram of sodium carbonate, 2 hydrochloric acid, a volume of 306 centimeter cube of carbon dioxide gas was formed and collected under standard pressure at room temperature, right? Standard pressure at room temperature, STP, right? Take the molar gas volume at room temperature, VM, as 24.45 dm cube. So we are actually given the VM now. So that means we can't use the 22.4. Right. So I did a hint on that to say that if you are not given, if you are not given, you can use the 22.4. If they say STP and you are not given, assume it's 22.4. But if you are actually given the molar gas volume, then you have to discard that one and use the one that you are actually given. Now they say the unbalanced equation for the reaction is this. Is it really unbalanced? They're lying. Okay. And this is not unbalanced. They were actually supposed to say the balanced equation for the reaction because they put the 2 and the 2 there. So this is balanced. Don't play with us. Nah. Then 5.3.1 says calculate the mass of sodium carbonate that reacted. Note that. Calculate the mass of the sodium carbonate. Sodium carbonate is this, right? So they even mentioned here. Now, the 1.5 gram here, in other words, if they say calculate the mass of the sodium carbonate that reacted, it simply tells you that the sodium carbonate is actually in what? In excess. And the 1.5 gram did not all react. Did not all react, right? Did not react completely. Yeah. So the 1.5 gram did not react completely, right? So that's what we are getting from this question. So learn to read in such a way that you analyze what's going on. So that means we can't use that 1.5 gram to actually calculate because this actually represents a mass that did not fully react or that did not completely react. So remember, when we perform our stoichiometric steps, we normally focus on the number of moles of something that reacted, or it should be a product if it's not a reactant. Remember that we know that a product is as a result of the reactant. A product is as a result of the limiting reagent. How many the amount of product or the maximum amount of product that will be produced will be determined by the what? By the limiting reagent. So if this one we say it's in excess, it means this one is actually the limiting. And this limiting reagent is the one that was responsible for actually producing that much of the carbon dioxide. So our first step here, step number 1, calculate the number of moles. We're going to ignore that one and then go for the product that was produced, right? Hence, we are also given that. So our first step will be the 306 centimeter cube. It's not in the desired SI unit, number 1. So we must convert it to dm cube. So 306 divided by 1000. And then we get that it is 0.306. Our VM is 24.45. And then when we divide that one, calculator, we get 0.0125. Allow me to round off to at least 4 decimal places with this one. So 0.0125 mole. And then step number 2, your stoichiometric steps still do not change. Remember, my subject of interest is what? Is the sodium carbonate. So I would have to say, compare this carbon dioxide to the sodium carbonate now, right? And then the ratio is what? 1:1, as we have confirmed that this is actually balanced, right? And then we're going to have this now, if this is 0.0125 and then the ratio is 1:1, meaning that we have the same number of moles. So we have done this a couple of times now. Now you understand that if the ratio is the same, the number of moles are the same. So now, to calculate then the mass, step number 3 is to calculate for the required value, which is what? The mass of the sodium carbonate. So to calculate the mass now, we are going to say N is equals to mass over the molar mass, which is 0.0125, and then mass over the molar mass. The molar mass for sodium carbonate, sodium is 23, so 23 multiplied by 2, plus 12 plus 3 multiplied by 16. We get that all of this will give us 106, this, right? And then multiply that by the 0.0125. And then we find that our mass should be 1.325 grams, right? Which if you wish to convert to 2 decimal places, it's 1.33 grams, right? So I'm just going to leave it like that because it's a terminating decimal. So 1.325 gram, right? So this is how you could have bagged yourself the 6 marks. Nothing difficult, just simply following the 3 stoichiometric steps that I constantly preach about. So 5.3.2 says, calculate the percentage of sodium carbonate in excess. So now it's revealing that the sodium carbonate all along has been in excess. But then by reading the statement, we were actually able to catch that. And also our calculation is proving that only 1.325 gram reacted out of what? Out of the whole 1.5 gram. So which actually tells us that the sodium carbonate has been in excess. So this was 5.3.1. For 5.3.2, only 4 marks. This is what we are going to do now. So we are going to say 5.3.2. Now, calculate the percentage of sodium carbonate in excess. They want the mass in excess as a percentage. So we want to say, what mass do we actually have in excess? To find the mass in excess, you'd have to say the mass initially, which is the one that is available, minus the mass that actually reacted. Then we find that the mass initially was 1.5 gram. But then from the 1.5 gram, only 1.325 grams reacted. So what do we have in excess? Meaning what would be left off after this is reacted? So it's only 0.175 gram. But we must then express this mass as a percentage. So percentage is this to the initial amount. So this would be 0.175 over what? The 1.5, and then multiply by 100. Let's find out what percentage mass is that to the total available mass. And then we find that we only had 11.67% in excess. That's all you do. So very nice question. 29 marks. 29 marks. Crazy. Crazy. Yeah. Let's proceed now. Okay, so we have the last question, definitely on acids and bases. Question 6 says a solution of potassium hydroxide, which is a strong base, is prepared by dissolving 3.36 gram crystals of that potassium hydroxide in 250 centimeter cube of solution. So again, what are we seeing here? 250 centimeter cube, not in the desired SI unit. And then they say define concentration. So what is that? The amount of solute, per dm cube of solution. Or others, they say per liter, right? Per dm cube, per liter, it's all the same thing because 1 dm cube is actually equal to 1 liter, right? The amount of solute per dm cube of solution. So straightforward like that. And then they say now, calculate the concentration of potassium hydroxide solution. Now, there are 2 formulas in which you can use for that one. You can either, so there are 2 schools of thoughts in terms of that. You can either go with the longer method, which is first you'd have to calculate the number of moles, which I don't really like this formula if I'm given the mass. So N is equals to mass over the molar mass. You take the 3.36 and then you say the molar mass of potassium hydroxide. What is potassium from the periodic table? Yeah, I think I've forgotten that one. So K 39. Okay. So don't actually be ashamed, guys, of looking at your periodic table if you have forgotten some of these ones. You are not supposed to cram them anyways. You're not supposed to memorize them, right? So you are always provided with your periodic table and also your formulas, guys. You are always provided with those. So 0.06 mole. And then from here, you can then calculate your concentration by saying the number of moles is 0.06 and then the volume is in a centimeter cube. So that means you'd have to convert it. So 250 divided by 1000, you get 0.25. And then now you'll get the 0.06 divided by 0.25, which will give you 0.24 mole per dm cube, right? So 4 marks like that, you'd get 2 marks for each of these formulas. But then there's the straightforward one where you just say, since I'm given the mass, I could just say C is equals to mass over the molar mass times volume, which if you can look at it, this is actually the same thing because here I just simply replace the number of moles here by the mass over the molar mass, which is what you are seeing here. Right, from this formula, the number of moles that you are seeing here, I just replace it by that so that it's just one formula. Then this is 3.36, and then the molar mass immediately there, 56, and then the volume immediately 0.25, which if you just punch all of this into your calculator, you get your 0.24 mole per dm cube without any hassle. Now, doesn't mean that if you use this one, you'll get lower marks than that one. Still the same thing. So if you use this one, they're just going to mark the formula substitution and then the correct answer. But with this one, probably going to mark like this, right? Yes. So either way, you will still get your 4 marks. Okay, now we are given 25 centimeter cube of potassium hydroxide solution of concentration 0.25 mole per dm cube completely neutralizes a dilute solution of sulfuric acid in a flask. The incomplete equation below represents the reaction that takes place. So they say the reaction is incomplete, but then it is actually balanced, right? So don't care about it being incomplete. We care about it being balanced. Define the term standard solution. Now, a standard solution is a solution of known concentration. This is a solution whereby the concentration is known. So straightforward like that, you just say is a solution of known concentration. So you must always have a way of sharing your definition in just the simplest way possible. Calculate the number of moles potassium. Calculate the number of moles of potassium hydroxide. So the number of moles of potassium hydroxide. So let's see, we are given the 25 centimeter cube volume, and then we are given this concentration, right? So we know with this one, we can just pull up the formula. C is equals to N over V. Then our concentration, 0.25, and the number of moles, our volume, centimeter cube, would still have to convert divided by 1000. So 25 divided by 1000, this gives us what? 0.025. When we cross multiply here, our number of moles will be what? So 0.00625 mole. It's a terminating decimal, so you'd have to write all of it, or maybe write it in scientific form, right? So for numbers that are this big, you can then write them in scientific form and say 6.25 times 10 to the exponent of -3 mole, right? So it helps because you still have it in 2 decimal places. Then calculate the mass of the sulfuric acid in the flask. So obviously for this one, we would have to apply our stoichiometry. So now we have already calculated the number of moles, meaning in answering 6.3.3, we'd have to start from step number 2, whereby we compare the molar ratios. Potassium hydroxide to sulfuric acid, the ratio is 2:1, right? Which means if this I have 6.25 times 10 to the exponent of -3, then what should be the sulfuric acid? It should be half of that. So 2x here is equals to 6.25 multiplied by 10 to the exponent of 3, divide both sides by 2, then my x would be equals to what? So that divided by 2 is what? 3.125 times 10 to the exponent of -3 mole, right? So you see that I'm avoiding having to round off now. And then from here on now, we can then calculate. So you see that we are on acids and bases, but then we are still applying stoichiometry. It's still part of stoichiometry, guys. Then this is to calculate the mass, we'll say N is equals to mass over the molar mass. Put our number of moles there. And then we have mass, and then the molar mass now of this is 98 here, and then we cross multiply. 98 multiplied by 3.125 multiplied by 10 to the exponent of -3. So this will give us a mass of what? 0.30625. So let's just say 30, right? Grams. So 30625 grams, which in 2 decimal places, we can just say our mass is 0.30, right? So, but then we can still leave it like that. Okay, so that's how you were supposed to do it. So all this question for 100 marks, right? So that's how you were supposed to go through all of that. Make sure that you use this video to practice and to gain knowledge on how to go through your exam papers. So, right. With all that being said, guys, you know what to do. Share the link with your friends and classmates so that they may also find assistance. You know, do not be selfish. We are winning as a team.